So I guess we can start. So good afternoon, everyone, and welcome to today's talk. I'm very delighted to introduce our speaker, Tom Zehle. Tom Zehle is soon starting in October his PhD at Alice Institute in Tübingen under supervision of Professor Frank Hutter, where his doctoral research is going to focus on specialization techniques for generalist foundation model. His work particularly emphasized prompt optimization, fine-tuning, and in-context learning, areas that are really hype and cutting edge in AI today. And previously, he was working as a data scientist in Airbus, and he was a master student at LMU. Together with Timo, who is also soon to be PhD at LMU, and Moritz, who is also going to soon to be PhD, but at TU Munich, he developed CAPO and Promptolution, exploring practical and cost-efficient approaches to automated prompt optimization. In today's talk, he's going to present CAPO, cost-aware prompt optimization, and the stage is yours.
Thank you so much for that warm introduction. So yeah, let's get right started into it. CAPO, cost-aware prompt optimization, and an introduction to prompt optimization and CAPO, which is a algorithm which we developed at LMU and MCML. So let's get started with the current state of large language models and generative AI. Currently, the LLMs are trained for general capabilities, such as reformulating emails, writing code, and they are also being evaluated on fairly general mathematical benchmarks. However, what we can see throughout the last few days or last few weeks, and what becomes more and more apparent in the research communities, is that we hit diminishing returns. The models are already trained at enormous scales for $100 million, and they are being trained for multiple epochs on an entire internet crawl. Maybe somehow synthetic data and reinforcement learning allow us to have some incremental improvements through the next few months. But as we see on the left on the graph, which is an evaluation on the GPQA score, the benchmark, we're somewhat hitting diminishing returns. Maybe this is just one example of a benchmark. For sure, there are also a few which are showing something contradictory, but in the future, at some point, we are going to hit a limit. So the question is becoming, how can we still further improve our LLMs? And I would like to argue that somewhat untapped potential is the specialization of LLMs for individual use cases. There are multiple techniques to do that, for example, fine-tuning. However, that's fairly expensive, requires a lot of data, and it also requires kind of hard labels for the training of the model. And once you have trained a model, you need to, for each of the use case, additionally deploy it. Another solution could be to utilize retrieval augmented generation. However, its implementation is somewhat complex, at least more complex than just having the vanilla LLM. It adds a lot of latency, and in many use cases, maybe we don't have the document information available at that kind of quality. So that kind of leaves us with a third option, which is prompt optimization. It is nice because its implementation and its deployment is somewhat straightforward, as we just need to change the input to the model. It can already function at low data requirements, and it also works for proprietary models, such as the ones hidden behind APIs. So, for example, we could also do prompt optimization on GPT-5. And whereas fine-tuning, for example, would not be as straightforward. There are two main techniques in prompt optimization. The first one of which is continuous prompt optimization, where we are basically putting the prompt into its embedding space and then doing in a continuous embedding space where we turn them into a learnable parameter and run, for example, gradient descent upon it. However, the outputs of these prompts are then not anymore interpretable as natural language. The second kind of which is discrete prompt optimization, where we directly optimize the natural language present within the prompts. And basically that allows us to use any LLM, whether it be hidden behind some paywall or if we're running it locally. And its outputs are inherently interpretable for humans. And this is also exactly why we are focusing on it throughout this talk. So to get some interactivity, I want to ask you the following question is, what do you think? Which prompt will perform better on a large-scale evaluation? So we have prepared this evaluation experiment on subjectivity, basically a task where the LLM is asked to evaluate whether a text is subjective or objective. In this case, we used a fairly large model, Llama 3.3, 70 billion. And I will give you some time to read through the prompts. And if you think prompt 1 is performing better, feel free to write a 1 in the chat. And if you're thinking prompt 2 is performing better, write a 2 in the chat, please. So I can already see, yeah, already 2 votes for prompt number 1. Maybe I will wait a few minutes longer, a few seconds maybe. Okay, so no votes for prompt number 2. Oh, Moritz may have seen the example already. So it's actually the second prompt that is performing somewhat better by actually fairly substantial margins, which is quite counterintuitive since it's not as detailed and somewhat short. Let me give you a second chance, this time on the GSM 8K dataset, where we have 2 fairly similar sounding prompts. So if you think this time prompt number 1 is performing better, write the 1 in the chat and prompt number 2. Yeah, for prompt number 2. Okay. So we already see 1 vote for prompt number 2. And I think I'm going to continue. Yeah, let's less verbose. Perhaps the LMN gets less distracted. Interesting. But it's actually prompt number 1 in this case. And to be fairly honest, we didn't find any kind of heuristics to see like, okay, maybe a longer, more detailed prompt works better than a shorter one. And for us, the takeaway was, okay, we really need to be careful when we are talking about prompt optimization and performing prompt optimization, as it's really not interpretable by humans too much. And the prompts are highly sensitive to some subtleties of the prompts. So, for example, in this case, we see 16 percentage points of accuracy drop just by choosing a similar sounding prompts. So for sure, it makes sense to optimize these prompts in a automated manner. So having motivated that maybe prompt optimization might be really interesting, we took a look at already existing prompt optimizers such as EvoPrompt or AllPro, and we found it's fairly expensive. So in this case, using modern LLMs such as GPT-5 or Gemini 2.5 Pro, we are getting prices for the whole evaluation run from $60 to $100, which is then only yielding us, basically a prompt for a single task. And of course, this is not viable in this large scale and it's not really making prompt optimization attractive, which is why we are continuing and setting up our own algorithm.
Okay, and I continue from here with introducing CAPO, our cost-aware prompt optimization algorithm. So we introduced CAPO on the and it's a novel discrete prompt optimization algorithm that enhances the prompt optimization efficiency, and we integrate therefore AutoML techniques and also integrate recent advances in prompt optimization. We also submitted this as a paper which got accepted at the AutoML conference 2025, which is next week in New York. So we're going to be traveling to New York next week. And we did this together with Professor Matthias Feurer from LMU. In general, CAPO is based on a genetic algorithm with LLMs as evolutionary operators. And we introduced 4 core innovations. So we introduced racing, which is an AutoML technique to save some evaluations when checking the performance of prompts. We also introduced multi-objective optimization to balance performance and prompt length. And we introduced joint optimization of instructions and few-shot examples. And we use task descriptions for improved robustness in the entire process. Okay, so I'm gonna walk you now through our algorithm. We first start with an initial population where we have as input some initial instructions and a pool of few-shot examples, which is just a subset of our data set we have available. Now, so this can look like this with the few-shot examples here attached. Next step is to do the parent selection. Here we select randomly 2 parent prompts from our initial population. Here the purple and the blue one. And then we go to the next step, which is the crossover. Here we combine the instructions using a meta LLM, and we do so by using a so-called crossover meta prompt, where we just give the task description. So in our case, this is a math task. So we describe it with this dataset consists of grade school math word problems and so on. And then we continue our prompt with the sentence, please merge 2 prompts into one single coherent prompt. And then we just insert the mother and the father prompt, and in the end yield then one merged prompt, which is similar, but it's crossover between those 2, like in every evolutionary algorithm. So we have now this crossed over prompt. And for the few shots, we just combine the few shots of the 2 parents and sample from them. So for example, here we're taking one of each and also append it to the prompt. And so now we have our crossed over prompt. Next up, we do the mutation step. For the mutation step, we also use a meta LLM to linguistically mutate the instruction. We also give a task description, and then we state that it should rephrase the prompt, preserving its core meaning while substantially varying the linguistic scale. And then we give the prompt to the meta prompt, and then we yield a new prompt with some words are flipped, so it's a little bit mutated. And to mutate the few shots, we also randomly remove, add, and shuffle them. So here we're adding, for example, a new few shot, and now we have our new prompt, which gets added to the population. So the last step, which is now left over, is to do survival selection. And in survival selection, we do this by doing a multi-objective optimization with a length penalty gamma. So we have our score for the prompt, but we subtract a penalty from it, which is weighted by a gamma, and the penalty is the relative token length, just to keep the prompts rather short and to penalize really lengthy prompts. And what we also do is that we introduce racing to save LLM calls by terminating evaluation early if it is significantly worse than other prompts. How can this look like? So this looks like here's a small example with our population of 5 prompts. In the first block, we use 30 samples and evaluate each block on the sample and get for each block a performance. If we now evaluate it on the second block, we can already see that the green prompt has not that good of a performance compared to the others. And we evaluate this with a statistical test. And if we can significantly state that this prompt is worse than the others, we can just kill it already here and do not have to race it through all of the blocks. So we continue racing with 4 prompts, can also kill the 4th prompt here, and are now left over with 3 prompts we can just use as our new initial population to restart the loop. And so in the 4th block, we do not have to do any evaluations. So you can see how we can save many evaluations by doing this racing and not evaluating on the whole data set here. Okay, now, but let's get us to some results. So we did extensive evaluations of CAPO on 3 LLMs. We used Llama, Gwen, and Mistral as LLMs, and 5 datasets, which were SST5, AG News, Subjectivity, GSM8K, this is the math dataset, and COPPA. We performed each configuration with 3 random seeds and compared the optimizers OPRO, Prompt Wizard, and Evo Prompt with CAPO. And as baseline, we also did an evaluation how good our initial prompts were. And overall, we can state that CAPO outperforms the other discrete prompt optimization methods in 11 out of 15 dataset and model combinations with improvements of up to 21% over the rest. So this improvement of 21% was in this case here where we did Llama on the GSM8K dataset, and you can see that all other optimizers are around 50% or even lower, while CAPO yields a prompt which got 73%. So really impressive performance here. Next up, we plotted the performance versus input tokens on the GSM8K dataset here using the Mistral model. And you can easily see that CAPO, which is the green line here, consistently dominates all other optimizers over the entire budget range. And what is also important is that the early performances of CAPO, so at about like 2 million input tokens, already exceed the optimizer's final performances after the full budget, and this also speaks for the cost efficiency aspect of CAPO. What we then also looked at was the performance versus prompt length, and what we can see here is that CAPO does yield longer prompts than Evo Prompt and OPRO, since they are really far on the left. We plot the prompt length on the x-axis here. But the CAPO prompts are much better in performance and still shorter than the prompts of Prompt Wizard, which are super lengthy. So we can see here kind of a trade-off between this prompt length and performance. And we also did some ablations. First, we looked at the effect of introducing the few-shot examples. So we saw that introducing few-shot examples improves performance, particularly for complex tasks like GSM8K. So it boosts the performance of here 13% in our case. But what we also noticed is that if we remove them, CAPO still outperforms Evo Prompt GA, even if it does not have few-shot examples available. So the whole improvement was not only due to the few-shot examples, but also due to the changed optimization loop. Then we looked at the influence of the length penalty, and we found out that dynamically more length was allocated to the more complex tasks. So if a task does not require a super lengthy prompt, we get down with the prompt length by making this length penalty higher. But for example, for a complex task like GSM8K, the prompt lengths are still quite high. Then we looked at the impact of our racing we introduced. So we saw that CAPO performs slightly better if we omit racing, but this is just within one standard deviation, so it's not by a far amount. But on the other side, with racing, we save on average 44% of our evaluations, and since we focus on being really cost effective, this is of course what we want to do, and this validates also the introduction of racing into the process. And last, we looked at the role of the initial instructions and did this by introducing some generic initial instructions which are not task specific and run the optimizers. And what we can see here is that CAPO is really robust against generic initial prompts thanks to the task description, because by incorporating this task description, it can still learn something and then figure out prompts by itself which work for the task. We can see this here on the right plot, where CAPO with generic initializations starts off not as good as the compared prompts with the not generic initializations, but it can keep up, and over the input tokens, after 5 million input tokens, it is on par with the performance. What we also can see is that Evo Prompt performance really stagnates with the generic initializations, so it doesn't really learn something and cannot learn anything if we don't do task-specific prompts. And with that, I hand over to Promptolution.
Yes, thank you. So now one important question remains. How do I actually implement prompt optimization for my own use case in practice? And that's what we tackle in the next part of this presentation by introducing Promptolution, a open source prompt optimization library, which we developed for exactly that purpose. And first, I want to start with why did we actually build such a library for prompt optimization? And that's because there are currently multiple issues in the landscape of prompt optimizers. So first of all, you basically only have implementation from some research papers. So it's quite a fragmented ecosystem in a sense that each optimizer is in its own repository, which resulted from some research paper with like different code interfaces, different coding styles, different dependencies. And so it's quite difficult to work with different optimizers and compare them if you actually want to benchmark against several prompt optimizers. Next, for these repositories, they often have quite hard-coded experimental setups. So if you have some use case which deviates from the paper's use case, it's very hard to do that. Often only classification is implemented, like this classical sentiment analysis stuff. But in practice, you usually have different use cases, and that's difficult then. And also the LLMs they used and how they used it is quite static. And if you have a setup differing from them, yeah, it's also quite complex to set this up. And lastly, and maybe most importantly, these research repositories, after the paper is finished, they are usually not actively maintained. So there are often quite some errors. There's no actual testing of the code. It's also difficult to understand because they often do not have a good documentation, and it's not quite robust against scenarios which deviate from their specific problems. So there are plenty of reasons to say, we have to implement some own thing, and that's what we did. We wanted to have some standardized library for prompt optimization with all prompt optimizers in one place with a consistent interface. So you can easily use them and replace one optimizer by the other. And our goal with this library is to build something like PyTorch, but for prompt optimization. So one standardized library which you can use for prompt optimization. Promptolution is designed in a modular way. We basically have 4 core modules: the LLM, a task, a predictor, and a optimizer. And I will, in the next slides, present them in more detail. But the important part is that we have different implementations for each component. So for example, different types of LLMs or different optimizers. And you can now easily switch them because they all adhere to the same interface. And what you also can do is to implement your own optimizers or tasks, for example, as long as you adhere to our base classes or interfaces. You can seamlessly integrate your own implementation into the ecosystem of Promptolution. We actively maintain this repository. I think our last new feature was like 1 day ago. If it's important for us that it's high quality code, we have over 90% test coverage and a comprehensive documentation, so it's quite easy to use. And for us as researchers, it was important that we enable large-scale reproducible experiments. For example, if you introduce a new prompt optimizer or want to compare prompt optimizers, you can easily do so with Promptolution, but it's also designed for practitioners. If you have a single use case in your company, you can also use Promptolution to do prompt optimization for this use case. Most importantly, our library is open source. And therefore, we also, of course, invite people who are interested in contributing to these libraries with their own specifications, own tasks, own LLM use cases, because our goal is to build up this kind of standard library for prompt optimization, not only us three, but together with the prompt optimization community. You can download Promptolution from PyPy, so it's a Python implementation. You can simply install it via pip. You can also find us on GitHub if you want to contribute or find more details. And as I already teased, we also have a documentation where we do not only provide the reference for the code, but also some tutorials for different use cases where you can learn how to use prompt optimization. So now I want to go through this component so that you get a little bit of better feeling how this all works together. And also in the course of that, I will provide a concrete example how to set up a specific prompt optimization use case. So the first component is the LLM. Of course, we want to optimize prompts for LLMs. This is a very important component. And the LLM component basically builds a unified interface to get a response from any arbitrary LLM implementation. And we also provide additional features like enabling concurrent calls and also, for example, token usage monitoring, which can also be quite important. We implement a lot of different kinds of LLMs. So first of all, API LLMs, so interfaces which enable you to make API calls to LLMs via the OpenAI client, which with that you can address multiple vendors, for example, OpenAI, Anthropic, or also Deep Infra, which are concretely implemented. And but you can also host your LLMs locally, so have your weights and runtime on your local machine using the transformers library, or what we did for CAPO, we used the VLLM inference engine to also use prompt optimization on a compute cluster. Now, as promised, we also want to take a look at a concrete example. And in our example, we start by setting up a LLM. In this case, we will simply use an API, namely the Deep Infra API, from which you can call, for example, a Llama 3.3 70 billion model. You just need to have an API key, and then you can simply use it with these few lines of code. Next, we have a component called the predictor, because we also want to extract a concrete prediction, which we usually want to optimize from the LLM's response. So this predictor wraps an LLM. And to give you a concrete feeling of how this can look like, we have, for example, the marker-based extraction. So your LLM usually gives you sometimes longer, sometimes shorter answer. For example, if you have a math task and ask it to reason about the task at hand, your answer might be quite long. For example, here, we have several reasoning steps, but usually for our prediction, we are just interested in this case, the final answer. So with the marker-based extractor, we only extract the answer between such tags here, final answer. So you can also quickly set up your predictor based on the previously introduced LLM. Next, of course, you also need to specify your task at hand. And the task component in our case holds the data and is also responsible for evaluating the prompts on this data. We support several task formats. The usual classification task, for example, sentiment analysis, or what we did in the beginning, classify between subjectivity and objectivity. But also, just recently introduced, we enable using LLM as a judge. So the basic idea here is to also be able to optimize prompts for tasks where there is no single correct answer, but rather subjective and creative. So you do not have a label, like for example in sentiment analysis, a true underlying sentiment, but instead want to optimize, for example, the creativity of a generated story, or you want to assess the helpfulness of a summary. So there are plenty examples where you do not have like a ground truth label. And in this case, the idea is to use another LLM, the so-called judge in this case, to assign a score to the output of the LLM for which we optimize prompts. So what you do in this case is, for example, we use this prompt for the judge. So we instruct it to be an expert evaluator and judge the quality of the prediction. So we provided a task description that it knows what the underlying task is, then the specific input we want to evaluate, and the prediction made by the other LLM, the quality of which we want to evaluate. Then you can specify in this prompt different criteria. And in this case, we wanted to return a score between -5 and 5. The good thing about this LLM as a judge is that you have very high flexibility. So as you can see on the right, we do not need like a ground truth label there, but you can also have that and compare against it. For example, in machine translation, you can also provide like a reference translation to which the LLM judge should compare the response of your LLM. And we also recently introduced a third task, which is the reward task, and addresses different problems. So now we address scenarios where you actually have an objective and measurable outcome. So for example, a concrete business metric, or you want to test, for example, for system compatibility. Does, for example, the output of the LLM work with your software? So in this case, you do not have labeled data, like for example in the classification task, but you also do not need a judge as a LLM as a judge to score your prediction. But as you have like a measurable business metric, you can actually specify in a reward function how this metric is derived. And this reward function is simply a function that takes the model's output as input and then returns a score for this output. So it's quite flexible, and you can optimize literally anything as long as it is measurable. For example, if you want to generate code, you can measure code execution success, you can measure API compatibility, and we also have an example for that one. So let's say we want to evaluate JSON parsing. So let's say our underlying task is to turn an article that you provide as input into a valid JSON file. And in this case, you can specify the reward function as if it's a serializable JSON format, you return a score of 1, and if not, you return a score of 0. And with that, and your data, which is in this case in this data frame df, and a task description, as Moritz showed for CAPO, for example, you can then specify your reward task. And then the last component, and maybe the most important for us in this talk, is of course the prompt optimizer itself, which has the task of running this whole optimization process, and after a specified number of steps, then returns the best prompts which it optimized during this process. We implemented 3 prompt optimizers in our library currently. So the first one is EvoPrompt, which is similarly to CAPO, an evolutionary algorithm, and also uses meta LLMs for crossover and mutation, but it does not only have a genetic algorithm, but also an initiation based on differential evolution. A little bit different idea is OPRO, which generates prompt through an optimization problem specified in natural language. So it also uses a meta LLM, which gets this meta information as natural language. So for example, a task description, examples, and also the previously generated candidates and how good they scored. And the LLM should then from this create new prompt candidates, which are then evaluated. And of course, we also implemented CAPO, our own prompt optimizer. So now let's continue our example, and of course we will use CAPO, our own prompt optimizer, and we want to optimize prompts for 12 iterations. As Moritz said, we need to provide initial prompts from where the optimizer can start. We can use very generic ones, which also works as we demonstrated in our paper, but we can also already start quite specific. For example, in this case, the first prompt could be translate the provided article into a serializable JSON format. And then we also specify how this extraction works. And of course, you need some more prompts to actually do this crossover and mutation stuff. Then we use the previously defined predictor and the task and these initial prompts to initialize CAPO. And as we saw, CAPO also uses meta LLMs to do this crossover and mutation. And for that, we can simply use the same LLM for which we also optimize our prompts. Then we optimize for 12 steps and get our optimized prompts with their scores back. That's one way to use prompt optimization, but we also have a more simple way to do that by the means of helper functions or so-called configs, where you do not have to specify each component on its own, like we did in this example. But yeah, which is a little bit more abstract and takes complexity away from the user, which could then be seen as a more beginner-friendly starting point, but can also be quite important if you set up large-scale benchmark experiments and want to do so in a structured and simple way. So you basically then simply provide a experiment config where you specify all the stuff we did previously in a little bit more standardized format. So for example, our optimizer, the initial prompts, the steps, the LLM specified by API and API key, for example. And based on such an experiment config, you can then simply use our helper function run experiment to run the whole optimization and evaluation. So it's a quite easy to use interface to do basically the same, but in a little bit more abstract and simplified way.
Yeah, thank you very much, Timo. And with that, let's conclude our talk today. I want to start off with talking a bit about the success stories that we've already seen for our prompt optimization initiatives. First one of which is that we are happy to see that CAPO and Promptolution start becoming adopted, and we already see some industry companies forking our library, for example, or creating issues such as Airbus, IBM, and Cisco. And we also got our first citation by SAP Labs last month, which evaluated enterprise APIs. Enterprise tool calling. And basically, they conclude that it struggles when multiple tools are available for the same task and the input parameters are somewhat ambiguous. They developed a solution based on CAPO, where they first created a pipeline that generates disambiguation-focused training dialogues and optimized their prompts and had a focus on fine-tuning these models to handle tool selection conflicts. Then they validated the performance for real-world deployment testing. And as we can see in this diagram right here, they saw some substantial improvements for their format correctness score by 5 to 15 percentage points. So I also want to give a short outlook for what we are aiming for with Promptolution and our prompt optimization initiatives throughout the next time. One of the things we want to implement in the future is a sort of a UI, which could be seen as a tensor board for prompt optimization, where we are displaying for the user the real-time optimization curves. The current state is really that you are sitting in front of the laptop for a few minutes and you're not getting really much information about what is happening and how well the prompts are improving. So that might be interesting. And also we want to display some example predictions that might also enable the prompt optimizer or the user of our libraries to understand better why certain prompts perform better and also to identify early if something is going wrong. We also want to deploy prompt optimization for retrieval augmented generation, but there are some certain questions. For example, what metrics to use? Do we mainly want to tackle hallucinations, or do we mainly go for optimizing the accuracy? So this is really a question where we need to talk to some more real-world practitioners. And another question is, of course, to what extent do we want to create synthetic data for this one? We also want to integrate our interface with DSPY and use some of the existing synergies. And so for those of you who are maybe not aware, DSPY is also a library that is somewhat focused on prompt optimization while being a little bit less focused on the automated aspect of things, while much more enabling the people to basically interacting with the optimization algorithm, already giving a framework in which they can optimize it and giving some constraints. A bit of a different and orthogonal, not really orthogonal, but a bit of a different direction. But I think there are really a lot of synergies if combined. We also want to start our research or contribute a bit on the further future research. For example, by starting with a Bayesian optimization ansatz. And we also want to take a look into extending our prompt optimization algorithm to agentic workflows. And we want to answer the question, why and how does prompt optimization really work? So we want to deploy some explainability algorithms for prompt optimization. And of course, what would be nice to see is if the real world usage can even be a little bit more increased and make it a little bit more accessible to everyone. Bless you. And we want to do that, for example, by providing a commercial API. So maybe someone is not interested in implementing and getting like a Python library and everything like that. Maybe they just want to talk to ChatGPT, and for that case, like, okay, just give us your prompts and we will return an optimized prompt for you. In this use case, maybe, for example, some of the end users are not really having data available, so we really want to evaluate what's the use case for synthetic data generation upon which prompts can be evaluated. So, what are the key takeaways of our talk today? First of all, the choice of prompts is really important and you should really optimize them. At least that's what we are arguing. We introduced our novel optimizer CAPO, which is outperforming at the point of writing, or which is outperforming the current state of the art at the time of recording this talk. And we introduced Promptolution, which allows for real-world adaptation. So please feel free to reach out if you have any questions, for example, via email or via LinkedIn. And if you have any questions, we are happy to take them.
Thank you. Wonderful talk. I already opened the project page and I will probably use it for my project. So we have a question in the chat by Thomas. The LLM as a judge also requires a prompt, right? Have you experienced with a case where you optimize both prompts jointly?
That's an interesting question. I think it's also a bit tangential to, for example, the meta prompts we are using. So basically, to give a short answer, no, we did not optimize those meta prompts, which we are, for example, giving to the judge LLM or the optimizing LLM, the so-called meta LLM, as we wanted, basically to constrain the problem first. But I think this is also definitely something to look a bit deeper into. As we've seen, there's performance to be gained by optimizing the prompts. So it would also make sense to do that on a larger scale. Whereas, of course, the issue is that it would be fairly expensive to do that, but I think it can be quite worth.
Yeah, I think there are also already works that jointly optimize the meta prompt and the prompts you really want to optimize. I think there's one important limitation if you also try to optimize the prompt for the judge, because then you basically change your evaluation metric. So it's similar to subtleties, changing subtleties in your evaluation metric, and then your scores are not exactly comparable anymore. So there are some mechanisms you need to be aware of then, but I think there's nobody who experimented with optimizing the LLM as a judge jointly. So maybe it would be worth to actually do that. Thanks.
Okay, there's one more by Edward. how would synthetic data help in this case? Would it again come back to the same question: clarity, structure, context formatting, etc.?
Yeah, interesting one. Maybe to separate it in two questions, how would synthetic data help? I think there are many use cases for LLMs where you do not have large amounts of data available, right? Like demonstrations of how you want to answer how the LLM is supposed to answer, or maybe it's not a classification task you're having, so you're not having ground truth. Basically, but for optimization algorithms, we need data to evaluate on. So I guess it would be helping in that sense that we can get scores for our prompts, even though you don't have any data available. And of course, the problem with that one would be how well does the synthetic data really represent the real world? So that would definitely be some research we need to do in that one. And of course, like question clarity, structure, context formatting. Yeah, I think also when we're generating the synthetic data again, yes, it would also, we need to be careful on how we are prompting basically the data generator, which could in turn also be an LLM in the end. Yeah.
Okay, another question by Jan. Great talk and impressive work. I understand you're interested in feedback from the industry folk building RAG systems. Should I just reach out via email? Probably so.
First of all, thank you very much for the warm words. And yes, please feel free to reach out, LinkedIn, anything. Yeah, it would be really cool to hear about that. Great.
Yeah, I shoot an email. It's very cool. Very great. Good stuff. And I see this having a relevance in our work.
Great.
Yeah, I shoot you an email.
That's exciting.
Thanks. Keep it up.
Thank you.
Okay, any other question? Okay, I think that's it for today. So thanks again for the great talk. I really enjoyed it. And for the audience, so see you in the next talk.
Thank you so much, guys.
Take care. Bye-bye.
Thank you.
Thanks.
Bye-bye.
Bye.